Good evening. Welcome to the live session of this NPTEL course, Waste to Energy Conversion. This is live session number 6. My name is Devarun Banerjee. I am a PhD PMRF scholar of Indian Institute of Technology, Delhi. So in this week's lecture, basically the anaerobic digestion is done. So the anaerobic digestion for biogas production, mechanism of anaerobic digestion, microorganisms for anaerobic digestion, pathways of them, different pre-treatment techniques of lignocellulosic biomass and wastes, flow sheet for anaerobic digestion of waste, uh, type of anaerobic digestion process, kinetics of methane formation, anaerobic digester and their types, operation of anaerobic digester, two-stage digester and process, impurities in biogas and their impacts, and sludge volume in a digester. These are the contents which are discussed. We will quickly check basically the contents. So anaerobic digestion are basically a series of biological processes in which microorganisms break down biodegradable material in the absence of oxygen. It includes important feedstocks, uh, including the energy crops, animal waste, industrial waste, MSW, restaurant food industry waste, sludge from wastewater treatment plant, like that. And it converts into the primary products like biogas, hydrogen, biofertilizer, compost, reusable water. So if we take the question, what is biogas? Biogas is basically a combustible mixture of gases which consists mainly of methane and carbon dioxide and is formed from the anaerobic bacterial decomposition of organic compounds in absence of oxygen. The major components of biogas are like this: methane, CO2, nitrogen, hydrogen sulfide, oxygen. And there are some other like typical contents of the methane and average dry matter content of different kind of Waste derived biogas are shown here. Uh, so the basic steps of anaerobic digestion are like this. The main steps are hydrolysis, acidogenesis, acetogenesis, and methanogenesis. And before that, we need to do the pre-treatment for lignocellulosic biomass. If we see the quantitative description of biomass degradation, there is about majorly 76% is the organic compounds are converted into short chain fatty acids. Among them, 24% is converted to hydrogen, 52% to acetic acid, and from them, by methanogenesis, methane is formed. And then the elementary description of anaerobic digestion is shown. So the basic stoichiometric equation, according to a scientist named as McCarthy, is shown here. This is basically your biomass is nothing but a hydrocarbon material, and it is hydrolysis is done. Then the biogas is formed like methane, CO2, some other like organic matter, uh, ammonium ion, and bicarbonate ion. So what is this C5H7O2n? It is basically the empirical formula of bacterial dry mass. And the initial one, the waste, as I told. So the some factors which affect the biogas yield are the solid or dry matter content in feed wastes, carbon to nitrogen ratio, temperature, pH of the solution, retention time, type of digester, microbes types. Uh, and then there are the biogas microbes groups, which can be methane forming or non-methane forming. The non-methane forming group includes the hydrolyzing fermentating bacteria, acetogenic bacteria, and methane forming are there, which includes the acetoclastic acetate degrading bacteria and other hydrogen neutralizing bacteria. And then there are details some of the roles basically of the microbes which are involved in the main three stages of biogas production are shown here. And the first stage, second stage, third stage, ultimately to form the methane. And further detail of different types of bacteria, hydrolyzing and fermenting bacteria, acetogenic bacteria, methanogenic bacteria, uh, uh, those are shown. Then if you see the pathways for fermentation, which includes one of the famous pathways is known as the EMP pathway, Emden Meyerhoff Parnas pathway, which is responsible for the production of pyruvate from sugar as an intermediate product, which is further converted to acetate, fatty acids, CO2, and hydrogen. At low partial pressures of hydrogen, acetate is favored. At higher partial pressures, propionate, butyrate, ethanol, and lactate are favored, generally in that order. And as we already discussed, like the primarily before all these steps, the pre-treatment of the lignocellulosic biomass is the most important. So these pre-treatments include some physical pre-treatments like milling, irradiation, or some other methods such as torrefaction, pyrolysis, hydrothermal methods. Why this pre-treatment is important? Because to increase the accessible surface, to decrease the degree of polymerization, to decrease the cellulose, and obviously basically to remove the lignin. Apart from the physical methods, some chemical and physicochemical methods are also there, like explosion, CO2 SO2 explosion, alkali pretreatment method, sodium hydroxide ammonia, acidic pretreatment, sulfuric acid, hydrochloric acid, gas with using gas NO2 SO2, and by using oxidizing agents, ozone, H2O2 like that. Apart from that, the biological pretreatment method is also there with the use of fungi and actinomycetes, which are also important. But though these are very much green process with low energy requirement, no chemical involvement, can be carried out at a very mild environmental condition, but their efficacy is not so much high. So ultimately, the purpose for which this operation is being carried out to uh, have a pre-treatment of the lignocellulosic biomass, that is somehow is getting affected negatively. So a very low treatment rate, and obviously due to that, it is not still yet considered for commercial applications. So some sample questions if you see. First question is, which of the following is not a primary product of anaerobic digestion? Hydrogen, biofertilizer, reusable water, bio-oil. So the correct answer is bio-oil. So bio-oil basically is the correct answer, which is not a primary product of anaerobic digestion. Bio-oil is a product of pyrolysis of lignocellulosic biomass. On the other hand, anaerobic digestion can yield all the other products which are mentioned here: hydrogen, biofertilizer, reusable water. So we have to match the following major component of biogas with their appropriate percentage: CO2, methane, nitrogen, oxygen, and the percentage is 0 to 1, 0 to 10, 25 to 50, 50 to 75. So the correct answer will be the first option. CO2 is about 25 to 50%, methane is about 50 to 75%, nitrogen 0 to 10%, and oxygen is 0 to 1%. And the major component composition of biogas. Hmm. So if we see the basic flow sheet of anaerobic digestion of waste, there is basically first the pre-treatments, which first initially it includes shredding, blending, pH adjustment, and pre-treatment of feed, and then after that anaerobic digestion via the bacteria, and then the digested effluent passes through some dewatering tank and then it is also treated according to the user requirement, and then whatever is there, that the useful components can be recycled back into the anaerobic digester, and the mixed gas which is being uh, generated, that is uh, passed to a separator where different gases are separated: methane, water, acid gases like CO2, H2S. These gases are separated. So there can be dry mode of anaerobic digestion or wet mode of anaerobic digestion. The dry is actually much simple technique. Basically, the solid liquid separation is very simple, whereas the wet mode is much more expensive. The dry mode is uh, having a more improved energy balance, whereas the wet one having a less improved energy balance. And if you see this total solid content in the dry mode, it is pretty high, about 25 to 55%. But in the wet anaerobic digestion, it is comparatively much lower, about 2 to 15%. And the type of feedstock accepted is uh, having a high flexibility for the dry anaerobic digestion, whereas for wet anaerobic digestion, it is uh, having a lesser flexibility. Okay, so the next question, with this we come to the next question. Generally, dash is the rate limiting step involved in methane formation: acidogenesis, acetogenesis, ethanogenesis, hydrolysis. The correct answer is the methanogenesis. So normally the methanogenesis is the rate limiting step or the involved in the methane formation. So if you see the overall different steps of methane formation are hydrolysis, acidogenesis, acetogenesis, methanogenesis. Among them, methanogenesis is generally the rate limiting step. So in anaerobic digestion, the presence of lignin decreases the rate of which step? Acidogenesis, acetogenesis, methanogenesis, hydrolysis. So the correct answer is hydrolysis. Presence of lignin basically decreases the rate of hydrolysis. Theoretical substrate conversion rate per unit reactor volume can be estimated as, these are the four options. Correct answer would be R equals to S naught nu max theta minus 1 minus Ks divided by theta into nu max theta minus 1. So R is basically the substrate converted per liquid volume at hydraulic retention time theta. Okay. S naught is the substrate concentration in the feed. Nu max is the maximum specific growth rate. Ks is the saturation constant. And these are the different uh, waste material. You have to match them with their typical methane content. Grass, corn silage, poultry waste, and the typical methane content 52, 68, 84 percentage. You have to match them. Correct answer is grass have 84 percentage of methane, corn silage have 68%, and poultry waste have 52%. Sorry, poultry waste have 68%, and corn silage have 52%. These are the basically list of different waste materials. So the other lecture discussed about the microbial fuel cell, energy-related cells, and fuel cell theory. Microbial fuel cell, its working principle, mechanism of electron and nitrogen transfer in microbial fuel cell, design of microbial fuel cell, microorganisms for this fuel cell, parameters affecting the performance of it, voltage and current calculation, types of MFC, and some efforts for improvement. And there are obviously different types of cells related to energy. Among them, microbial fuel cell is a fuel cell in which chemical reaction is replaced by microbial reaction and the organic load of wastewater is used as fuel. Now this is a basic schematic diagram of a double chamber microbial fuel cell in which this anodic and cathodic chamber are there. where anodes and cathodes are there, where two reactions are happening. It is separated by a membrane. Operates via electron transfer mechanism. So there can be indirect transfer through externally added mediator or through self-excreted mediator. Okay, so these are the examples of indirect electron transfer. Apart from that, there can also be direct electron transfer, and the movement of this entire cell, microbial cell, it happens. Electrochemically active redox proteins such as cytochromes are present on the outer membrane, which can transfer electrons directly to the anode. So the typical components of a microbial fuel cells are cathode, anode, photon exchange system, and electrode catalyst. Electrode catalyst involves polyaniline electron mediator immobilized on anode, platinum black, manganese dioxide, Fe3 plus. Different metabolic paths are such that oxidative metabolism, fermentative metabolism, oxidative metabolism like direct and indirect, fermentative metabolism can also be direct and indirect. These are basically based on different bacteria and microorganisms. Okay, some parameters which affect the microbial fuel cell operation are electron material, pH buffer and electrolyte, photon exchange system, operating conditions in the anodic chamber, operating conditions in the cathodic chamber, type and composition of substrate, type of oxidant used in cathodic chamber, presence and absence of catalyst. Then another important aspect is the current and voltage calculation. So basically, the current collected at an electrode is obtained by integration of all possible local current densities Ij over the electrode surface, and the charge produced is calculated from the integration of cell current over time. Q equals to integration of IDT. I need to integrate it over 0 to t. Further, some voltage and current calculation, basically some basic fuel cell things are shown here. Basic equations can check about the voltage, about the Ohm's law, basic V equals to IR, and that total cell voltage calculations. And obviously, again, you have to calculate the voltage current. You have to also take into account the losses in the microbial fuel cell. And there can be different types of microbial fuel cells, such as single chamber, double chamber, flat plate, membraneless MFC, upflow MFC. Like now the galvanic one. Now the questions: galvanic cell is used to convert electrical energy into chemical free energy, chemical energy into electrical energy, mechanical energy into electrical energy, none of the above. So the correct answer is chemical energy to electrical energy. Galvanic cell converts chemical energy to electrical energy. Electrolytic cell converts electrical energy into chemical free energy. Batteries are basically the devices which carry out this conversion, and fuel cell is an electrochemical device in which free energy of a chemical reaction is converted to electrical energy. And the last lecture of this week was about fermentation. Fermentation and energy production. Production of ethanol from three different feedstocks and pre-processing steps. Production of ethanol from starchy crops, corn. Production of ethanol from lignocellulosic biomass. Pre-treatment of lignocellulosic biomass. Detoxification hydrolysis is on the some topics which are covered. If you see the fermentation, uh, fermentation is a metabolic process which converts sugars to acids, gases, or alcohol. So from syngas, which is formed via gasification from organic waste or biomass. In syngas, via fermentation, ethanol is formed. Ethanol is basically projected as a alternative to gasoline, alternative to petrol as a biofuel, renewable fuel. Mm, ethanol, as you can see, like so, fermentation is a series of chemical reactions for converting sugars to ethanol in the presence of suitable microbial strain which feed on the sugars. Okay, so ethanol and CO2 are produced as the sugar is consumed. Simplified fermentation reaction for a 6-carbon sugar glucose is as follows. So these are the basically often the fermentation. There's some recovery section is also there, like distillation and dehydration. After that, the ethanol is actually formed. The ethanol concentration in fermented mash can attain a level of only 4 to 10%, depending on the operating conditions and the strain of yeast being used. The type of yeast being used, depending on that ethanol concentration in the ultimate fermented mash, which uh, can vary. So an important point is to make ethanol fully miscible with gasoline. It is necessary to further remove the residual water to produce anhydrous ethanol with a concentration of at least 99.5%. To attain this concentration, the hydrous ethanol has to undergo a suitable dehydration process or operation. So there are basically this again the wet process, the dry process, basically as a part of the fermentation technique to produce ethanol, which is the commercially available technique by which bioethanol is actually formed. But nowadays, the catalytic production of ethanol is actually also being focused upon, because the biological process is actually very much slow process. So even though it's a very much greener process, it can be carried out at less energy consumption, but the reaction rate is very slow. So to make a faster reaction, because when the ethanol is getting commercialized to be blended with gasoline, to be uh, you know uh, used in the commercial vehicles transportation sectors, then it would be required to produce more and more, and high amount of ethanol production would be required. So in that scenario, it might be a challenge to tackle that high demand of this kind of biorenewable biofuel by only the biological process, biological production route. Rather, even though coming at a bit of like energy intensive process, the catalytic chemocatalytic process or the thermocatalytic process might be a good option. So some common lignocellulosic biomass if we see, the industrial waste, forest biomass and waste, municipal solid waste, MSW, agricultural residues and agro waste. These are the common lignocellulosic biomass which can be converted into different, ultimately to ethanol. So for that, some pretreatment technique is required. Pretreatment technique is basically applied to remove the protecting shield of lignin and hemicellulose, make the cellulose more readily available for enzymatic hydrolysis. Because this lignin and lignin is much more recalcitrant in nature, so it does not react very easily under very harsh conditions, under very much mechanical and thermal force we give, then this lignin part can react. Okay. So energy efficiency of any pre-treatment process can be determined from total sugar yield and energy consumption during the process. The pre-treatment energy efficiency is the ratio of total soluble sugar yield and total energy consumption during the pre-treatment. Now, favorable characteristics of pre-treatment processes. So, an ideal case would be no loss of sugar, no degradation of sugars or sugar-derived products, avoiding destruction of hemicellulose and cellulose. Only selectively lignin should be removed or separated. Obtainment of cellulose with high digestibility, production of minimum amount of toxic compounds, no requirement of biomass size reduction before pretreatment. And already discussed some physical process, chemical process, physicochemical, biological processes are there for the as the part of the pretreatment technologies. Okay, and with this, we check last couple of questions. So DASH is a metabolic process which converts sugars to acids, gases, or alcohol. Fermentation, anaerobic digestion, pyrolysis, gasification. The correct answer is fermentation. Fermentation is a metabolic process that converts the sugars to acids, gases, and alcohol. And the last question is, depending on the operating conditions and the strain of yeast used, fermented mash can attain a level of around how much percentage of the ethanol concentration? 4 to 10, 10 to 20, 20 to 25, and 20 to 30. Correct answer is 4 to 10%. So the fermented mash, depending on the strain of yeast, ethanol concentration can be in between 4 to 10%. Okay, so that's all from my side. Thank you.